Welcome to this introduction to the Lumissil IS32CG5317 Evaluation Kit. The CG5317 is a reliable, low-power HomePlug Green PHY communication transceiver. It's a single-chip solution with an embedded analog front end requiring a single 3.3-volt rail. HomePlug Green PHY is a standard specifically for low-power communication over power lines for electric vehicles, electric vehicle charging stations, smart meters, and other smart grid applications. The CG5317 provides the power line communication interface, as well as SPI and Ethernet interfaces to the host processor. It's the physical layer, or layer 1 in the OSI model. The CG5317 has many diagnostic capabilities, such as signal-to-noise ratio, gain, and various statistics. It also has an embedded process voltage and temperature sensor and the ability to stream data logs to the host processor. It's available in industrial grade and an automotive grade AEC Q100 certified option. And to top it off, Lumissil provides a support portal for all your hardware, software, and communication development. The CG5317 Evaluation Kit provides everything needed to set up a HomePlug Green PHY network between a vehicle and a charging station. It starts with two full-featured HomePlug Green PHY modules. One is configured as a charging station, and the second is configured as an electric vehicle. The kit also includes two power adapters, two SD cards that store the host MCU operating systems, two micro USB cables for UART debug of the 5317 and the host MCU, an SMA cable for single-ended Green PHY interface, and terminal blocks for a differential Green PHY interface, and 2 gigabit Ethernet ports. Internally, the kit provides JTAG debug interfaces for both the CG5317 and the host MCU. In addition to the evaluation kit, you can go to our host website and download the software development kit and the hardware development kit. The software development kit contains the host library, sample code, the Linux SPI drivers that emulate an Ethernet-like interface to the CG5317, and gives you access to all of the configuration and diagnostic registers. Be aware that you will need to provide the vehicle-to-grid stack that applies to your specific application. The vehicle-to-grid stack is specific to the vehicle or charger and negotiates the charge rates, battery health, billing, etc. Also included with the SDK is perhaps the most impactful tool that Lumissil provides, and that is the Amplitude Map Calibration Tool. ISO 15118-3 requires the power spectral density of the signal to maintain a flat -75 dBm per Hertz across all 1,155 subcarrier channels. This tool enables you to automatically correct your power spectral density, and this can be a huge time and money saver when dealing with the various forms of noise and interference while attempting to route cables inside a vehicle or charging station. PSD calibration is done by adjusting the power level of each operational frequency. To accomplish this, the 5317 has an embedded traffic generator that can generate traffic suitable for measuring the PSD. Simply connect a spectrum analyzer to the line, for example the inlet or the outlet, run the traffic generator, and take your measurements. You can then export the measurement data as a .csv file and load it into the Amplitude Map Calibration Tool. Details for setting up the spectrum analyzer and exporting the data are included in the documentation. The interface to the calibration tool is created in Excel, which allows easy importation of the configuration and spectrum analyzer data. On the main page, you can see the parameters that make up the configuration file. Included in the SDK are several sample configuration binaries. Let's load the SPI Central Coordinator sample. You can modify the parameters here and notice the pop-up windows that give you a description of each parameter. Now let's get back to the amplitude map corrections. Select the tab labeled Calculated Amplitude Map. This is where you can load in your spectrum analyzer data. I'm going to load in a sample data file so we can see how the amplitude map corrections are made. You can see there is quite a bit of variability in the PSD column and on the graph. To fix this, we're going to select a target output power of -75 dBm per Hertz to conform to ISO 15118-3. Then we'll click the Calculate Amplitude Map button. Now you can see that the attenuation corrections have been filled out, and a new graph is created with the corrected amplitude map. We can go back to the General Parameters tab and create a new configuration binary that contains the PSD corrections along with the configuration settings. This binary can be stored in external flash connected directly to the chip, but more commonly, it's stored by the host processor and loaded into the CG5317 via SPI or Ethernet. To make a configuration binary, enter a file name and click the GenConfig button. Now let's power up the two boxes and step through just a couple of the operations available in the Evaluation Kit's host processor software. To get started, make sure you have the FTD driver for the USB to RS232 adapter, TeraTerm or a similar terminal application, and WinSCP for the SSH file transfer protocol in order to access the host MCU's file system from your PC. Links for each are provided in the documentation. The manual contains a quick start guide to show you how to configure your network interface card with the proper subnet and IP address. It will also help you configure the baud rate and other settings to connect the terminal application. In this picture, we see all the necessary connections. From left to right, we have power, Ethernet cables connected to the PC or router, USB to COM port connections, and the included coax cable connected between the two boxes. The CG5317 boots up and is ready in under a second. What we see here is the host processor booting the Linux operating system. We'll get a command prompt when the host is ready. To determine which box is the EV and which box is the EVSE, we can run the interface configuration command ifconfig in the terminal. The central coordinator will have the IP address ending in 101. The station will have an IP address ending in 102. In order to reliably perform an association of an electric vehicle to the supply equipment, you can use a special feature called Signal Level Attenuation Characterization, or SLAC. When SLAC is invoked by a client, it broadcasts a series of sounding packets. Stations within range compute the average received power for each packet and report this information back to a designated MAC address. The results are compiled and the station with the highest received signal strength can be identified. There are a couple of commands you need to establish SLAC. I'm showing them here briefly, but know that all the commands and explanations are included in the documentation for reference. Run the EVSE.ini command in the central coordinator and the PVE.ini command in the station. Once the central coordinator gets its match confirmation message and the station receives the set key confirmation, the devices have completed the SLAC process and a 1-hour charging session begins, after which the devices will disconnect. An AV logical network can be formed by two stations with identical network masks and security levels. You can set the network masks using the following commands. These commands are listed in the Quick Start Guide for reference. Now we can run traffic between the two devices using iPerf. iPerf is a tool for measuring the maximum achievable bandwidth on IP networks. Run the iPerf command on the station and on the central coordinator to determine the bitrate and jitter. This concludes this introduction to the CG5317. Please visit our website or contact one of our representatives for more information.